All right, so kind of our like nearly third last lecture for the term is a lecture on software complexity. It's the last design lecture that we do. It's not really it doesn't really have anything to do with the project. It may come up on the exam, but it is certainly very interesting. And this lecture is essentially about we need a way to talk about and analyze how complex software is. You know, because communication is really important. And if we don't have a way to actually have a conversation about things, it's very hard to get better ideas. And what I mean by that is, if someone says to you, hey, is your software complex? Like, what do you even say to that? You know what I mean? Like, what do you say? I don't know what I'd say. Well, I know what I'd say because we're about to have this lecture, but I wouldn't have known what I was going to say in my second year of uni, is the point. And we're going to cover two main topics. One's quite theoretical, one's mostly theoretical, a little bit fun. The first one is accidental versus essential complexity, kind of comparing and contrasting these two fundamental ideas of what complexity are. And then the last one's on some kind of analysis or measurements, which is on something called cyclomatic complexity, which is about looking at how complex software is and putting a number on it. So first thing, what is software complexity? You know, if I could ask all of those here live to define what software complexity is, what would you say? What would you say if someone asked you what is complex software? Dylan says how complex software is. That's a terrible definition, but I appreciate the effort. Does many different things. Yeah? Are you complex if you do many different things? It's a good question, right? But my throat's starting to go again. Essentially, when we look at software complexity, one way of dividing it up, which is the way that we encourage you to divide it up, is into two big categories, right? And it's what we call essential and accidental complexity. Anthony says that software complexity is how easily understood a software program is. Yeah, that's one way of looking at it. What's more interesting is that, and this is kind of where this slide's getting to and where this topic's getting to, is that if software is hard to understand, it's pretty easy to tell that it's complex. But a distinction that's quite relevant for us is the difference between what we'd call essential and accidental complexity. An essential complexity is any kind of complexity that we feel is inherent to the problem at hand. For example, if you have a project backend, like your major project is, and someone says, how complex is it? And you say it has 40 routes. They go, wow, that sounds complex. And you're like, yeah, but it's essentially complex. Like, it's essential that it's that complex because that's the scope of the work. Whereas accidental complexity is complexity that's not inherent to the problem. It's essentially complexity that has been introduced that didn't need to be introduced to solve the problem. And for example, that would be writing your own JSON parser, or finding a really convoluted way to encrypt stuff. Maybe you've written a hash function instead of using a library one. It's any time that software becomes harder to work with, harder to understand, harder to maintain, when it just wasn't really necessary for that to be the case. The reason that this distinction is important when it comes to conversation is because essential complexity basically can't be removed, but it can be managed with good software design. So what that means is that you can't really prevent needing 40 routes for your project, or however many there are. But what you can do is you can write your code and design your code in a way that is more elegant and more maintainable. If we go back to that week 5 lecture where we talked about, writing maintainable software. Whereas accidental complexity can basically just be mitigated outright by better engineering decisions, like the smart use of libraries. it's really easy to remove a lot of accidental complexity. That's what senior engineers are good at. It's what experienced engineers are good at. It's what teams of people will generally, you know, come together with, and someone will come up with the idea. But it is hard to remove entirely because it's in all of our nature to add accidental complexity to all problems, right? It's just like bad design. It just happens. It's a question of whether it happens a little or a lot. There are some questions that don't necessarily have answers that we try and leave students with a little bit. One of the most interesting questions is there an easy or scalable automated way to distinguish between accidental complexity and essential complexity? It's a good question. Not really at the moment. Will there be in the future? Maybe. And to what degree, if we can identify it, will accidental complexity be removed in the future? That's just something to think about. You know, we might have more tools in the future that can do this for us. You know, 10 years ago, linters weren't really a thing. You know, nowadays we have that kind of code stuff that can autocomplete. There's a lot of crazy things that can happen now. So that's just something to keep in the back of your mind. But that was essential and accidental complexity. Really easy topics. The second part of this short lecture is on measuring complexity. So if we pose the question, how can we measure software complexity? What we generally might want to measure is how coupled a piece of software is. Remember, again, like we looked at like coupling and cohesion. Coupling was the degree to which independent pieces of software are joined together, which we want to avoid, and cohesion was the degree to which similar pieces of software were joined together, which we want to keep. But then we have cyclomatic complexity, which is a whole new idea that we haven't covered yet, which I think we do in a sec. Yes, sorry. I thought we talked about coupling and cohesion. I think I actually covered this much earlier than normal. I don't think we had this much detail on the slides, but just a quick recap again. Coupling, measure of how closely different software components are. So just to reiterate from week 5 lectures, if you have an auth library and like a channels library, they're different. If they're coupled, it means they're kind of joined together, which you don't want them to be. So we want to have low coupling or loose coupling. Coupling is of different software components, whereas cohesion is the degree to which elements of a module belong together. So essentially, if you have, channel details and, channel messages, they're kind of very similar. So you want them to have high cohesion. You want them to stay together. So Nikhil says it's like how interdependent they are. Sort of. It's basically saying it's really honestly a bunch of waffle in the sense that all we're talking about with coupling and cohesion is that things that are different should be apart and things that are similar should be together. Right? You get this. In the fridge, you put your drinks in the shelf and you put your fruit and vegetables in the crisper. It's good if you keep things that aren't similar apart and things that are similar together. That's all we're talking about here. But cyclomatic complexity is a new idea, and cyclomatic complexity is the measure of the branching complexity of functions. So it's a way to measure how complex functions are, but in particular, it's about their, how to put it? Back when we did test coverage 2 weeks ago, we talked about how you can do coverage on lines or coverage on branches, where branches was all the different ways that software could break off from one another. Cyclomatic complexity is the measure of how many different kind of if statements, while loops we have in our functions, because what it's focused on is computing the number of linearly independent paths through a function. And it's actually a pretty simple thing to calculate, and there's this formula here which is going to make no sense until we go through some examples, but basically what you do is you take a function, and we're going to do a few of these together. You convert it into a control flow graph. You essentially diagrammate it. You turn it into a diagram, and then you use this function to calculate the cyclomatic complexity, where E is the number of edges and N is the number of nodes. And here is an example of a function here. So if we take a function like this one, And, you know, let me take a screenshot of it. Can I just right click? No, it's alright. Screenshot. So let's take a screenshot of this. What we can actually do with a function like this is we can actually try and trace the flow through this function by highlighting a bunch of the different branches. And what I mean by that is, let's say that this function starts up the top here. And what we're going to do is we're going to explore what are all the different ways that we can move through this program. Well, this program is pretty simple because when you start the function, you can only ever go through the if or the else statement, right? So I could call this one here, like, I might call this one like my start, and this is the if, and this is the else, right? And there's only two ways I can go through it. I can go through the if or the else. And once I'm in the if, well, what am I going to do next? I'm always going to have to go through this line of code that has the be function on it. Yep. And when I go through the else, I'm always going to have to go through the line of code that has the C function on it. And whether once I do B or I do C, in the case of B, well, I skip the else. In the case of C, I never go through the if. So both of these take me to the end of my program here. This is the end of my program. Yeah, so that's the program finishing. Now what we do, once we have a graph like that, is we apply our formula, which is e minus n plus 2. So e in this case is the number of edges, which is, you know, the lines, 1, 2, 3, 4, 5, 6. N is the number of nodes, which is 1, 2, 3, 4, 5, 6. And then we say e minus n plus 2, which is 6 minus 6 plus 2, which is 2. So now we know that the cyclomatic complexity of that is 2. Right? And a low number is good. Generally, the higher the number, the worse it is. The higher the number, the worse it is. The lower number, the better it is. And we can apply this to many different examples. But actually, before we do that, let's just take a quick pause and be like, hold on a minute, Hayden. What I drew is different to what the solution is here. And the reason for this is actually quite interesting and simple. There's no correct way to represent your code diagrammatically because you're representing branching, and cyclomatic complexity actually represents branching. And what I'm saying with this is that this whole B thing we added here is kind of unnecessary. You could have kind of skipped this and just had the program do what the kind of answer has over here. But the reason it doesn't matter that we added those extra things is because it was a linear flow. So I added these extra steps which didn't affect the cyclomatic complexity because cyclomatic complexity is measuring all the different branching factors. And in this case here, this moving through the B thing was not it wasn't like a decision point. Like if you enter A, you're always just going to do B and then move on. It's always linear. So when we add an extra node, we just added one extra line, and we added 2 extra nodes that were unnecessary. So we added 2 extra lines that are unnecessary. So when we did the calculations, 2 extra nodes, 2 extra edges, they kind of cancel each other out. So don't be scared about drawing this wrong. And if we move on to another example here, before you look too heavily at that diagram on the right, let's try this one as well. So in this case here, well, Nikhil, yeah, if B has 2 branches within its function, we'd have to show that. And I think we kind of have this here, so this might answer your question. Let's say that we have our start up here, right? We have our starting point. Now from our start, we can either go through our if or our else. Now I might write, how you annotate this is up to you. I'm just going to write if here, and then here I'm going to write else. And once I'm inside the if, well, I'll keep my things consistent. We're going to call the B function. And if I'm in my else, then we can do one of 2 things, which is we can either go through like another if, like that, or we can skip the if. I don't really know where we go if we skip the if. But if we go inside the if, we're going to call the D, like that. And if we skip the if, we're not going to call the D, but these things will end up in the same place. You know what I mean? Like they'll finish at the same place. And if we go call the B function, they're all going to finish at the same place now. They all kind of come down here. I should probably draw that a little bit differently. They're all going to kind of finish at the same node in the end, which is like our end point. End. Anyway, I'll just write smiley face for the end. So now, if you have a look at this diagram, you can see a few things. Anything that's totally linear was unnecessary. So in theory, I don't really need that. And in theory, I don't really need this. But it doesn't matter, because you can always draw redundant things in and the math will come out the same. So what is it? E minus n plus 2. Well, E is, what do we got? 1, 2, 3, 4, 5, 6, 7, 8. We got 8 edges. How many nodes do we have? 1, 2, 3, 4, 5, 6, 7. Plus 2 is 3. Cyclomatic complexity is 3. Obviously, this diagram's drawn differently. These diagrams are very like slimmed down. So that's another example there. We have another cyclomatic complexity example. I think we got 4 to go through together. So we got this while loop here. This one's kind of easy if you think about it. We have our start up the top here. Then from the start, well, we're always... This is where it gets a little bit tricky. Oh no, we're always going to go through the while loop, I guess. Because you always have to call it once. Maybe I'll get this wrong. We'll find out. So you kind of have this, yeah, you can either go through the while loop, or you can go straight to the C. So I guess you always have to go through the while loop, I think. So we're going to go into the while loop, and then from the while loop, we either kind of come back into the while loop, or we go to the C, and we always finish at the C, and then from the C, we like end our program. Let's see if we got that right. I probably screwed something up. Yeah. How many edges we got? 1, 2, 3, 4. We got 4 there. It's not 2, is it? Oh, it is 2. Okay. Well, there you go. This is what I mean. Don't get too caught up. Like, as long as how you're drawing it makes sense, you'll kind of be okay. In this case, we had 4 edges, 4 nodes, and we got 2. I've never drawn it like I did today. I don't know what compelled me. I don't think it really matters, because obviously you can think you either enter the while loop or you don't, but what I drew here wasn't really, like, this was the entering the while loop part. Because you kind of, like, I was kind of thinking, well, no matter what, whether you enter the while loop or not, you still actually have to execute this line of code here. So this A here, this is technically like the A function that I was drawing. And then, like, if you enter the while loop, you're going to have to enter, you know, call the A function again, you know, so you're always going through that. But I hope that's not invalid. Anyway. And then the fourth example, this one's a bit more involved. Sorry. Oh, God. I feel like I'm dying. Not literally. It's a bit dramatic. Okay. We have this function here. Well, similar kind of thing again. Sometimes I find it really easy to annotate the functions, actually, where I say, you know what, let's call this A up here, like where the function starts, and then we can like enter the while loop here, which is like B, and then once you enter it, you can go inside the if statement or the else statement, and once you're inside this if statement, you can, I guess, go to E potentially. And then let's call F the end of the program. We could try something like that, where I write like A, and then we could try drawing in a different way. B, F, C, E, D. We could do something like this. Draw little circles around all of them. F's quite sad down there. Yeah, so from A, we can either say, like, go through the while loop. Let's, like, visualize it a different way. Or we can just, like, totally finish the program. Once we're in the while loop, we can either go inside the if or the else statement. Easy enough. And once we're in the else, we just end up going straight to the end of the program. And then once we're inside this if statement, well, we can either go from C to E. Or if we skip that if, we go to the end of the program. You know what I mean? Like, it all kind of, you just kind of follow the flow. And then again, we do what we did before. We count the edges. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 edges. We have 1, 2, 3, 4, 5, 6 nodes, which is 8 minus 6 plus 2, which is 4. The answer is 4. So there's our cyclomatic complexity. Now, as you can see, the higher this number gets, the more complicated the function is. So you can start to see how this can be a semi-useful measure. That's what it is useful for. Oh, we have another example here. It's the same thing as what we saw before. I won't drag you through this one, but same gist. You start at the top. You either go... Sorry. How is this drawn? Yeah, I guess this one's like treating the top like the while loop. You either like skip the while loop and go to the end, or you enter the while loop and you go through one of the if or the else's. The if and the else's take us both here, and then you finish it. And this is a really good example. Like this diagram actually has some redundancy in it, because like technically, like again, any linear flow can be cut out. See, these two are linear, these two parts. You don't kind of need that there. You could kind of like rub this out and just draw a line straight through like that, and it will give you the same answer, but same kind of thing. So the benefit of cyclomatic complexity is it's a simple, measurable way to understand function complexity. You know, and it's a good way to talk about it because, you know, if you're working, and I'm sure there's automated tools out there that can figure this out. I haven't used one personally, but it's a great way because you can kind of nearly mandate within an organization to say that, you know, no functions should have a cyclomatic complexity of more than 8 or 10 or 12 or 6 or something like that. It's a way to kind of keep your functions simple. One of the problems with cyclomatic complexity, two things to think about. One is that measuring cyclomatic complexity assumes that non-branching code has no complexity. So it assumes that like a 100-line function with no ifs, elses, or whiles in it is simple, which it's not always. And sometimes functions can actually be better to kind of have a high cyclomatic complexity. Sometimes breaking functions up unnecessarily into smaller pieces can make code harder to read. And we can calculate it automatically. If you Google, you know, I don't know, NPM cyclomatic complexity, there's probably a library for it. Don't know. I haven't looked this up before. Yeah, complexity report. Sometimes they might not necessarily use this exact measure, but this whole lecture is more just to try and make you think about that there are automated ways to try and analyze the complexity of software. I'm not sure if this one... Yeah, what is cyclomatic? Oh, there you go. Specify the per function cyclomatic complexity. It's all here. This would be fun to play around with. And that's it. There's some further reading if you'd like to read it, but otherwise, please leave some feedback on this lecture. And hope that was interesting. A little bit of a tidbit on software design. Lots to think about. So pause and thank you.